Hey all, this is Derek, and we're starting off chapter 5, which is going to be about quadratic functions primarily. But before we get to do quadratics, we got to look at a new version of numbers that we haven't looked at least in this course, which is complex numbers. And quadratics we're going to see are kind of those U-shaped parabolas. You may have seen them in a previous course. You probably did see them in a previous course. And if I draw a parabola, I can make it equal 0 twice. I can have two x-intercepts there, two solutions. If I draw it really careful, I can have it come down and just kind of bounce off and have one solution. So these are like two real solutions. This would be one real solution. But I could also draw a parabola that doesn't have real solutions. But that doesn't mean that when I go to solve that, it'd been better if I had drawn it right there, pretend that one. When I go to solve something like that, I get kind of a weird thing, which is when I bring this 4 over, I have something squared equals a negative, and that can't happen. And so all along we've been saying this doesn't have solutions. When I look here in the real plane, it doesn't have solutions. And what our first topic is, complex numbers, is how we're going to handle this issue right here, which is we're going to define a new number. And that number is going to be the imaginary number I. And it is that whenever we run into a root -1, we're going to call that I. Much in the same way when we see 3.14, yada, 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 that number that, is the ratio of the circumference to diameter of a circle, pi. So we call that pi because it's convenient. We're calling this I for imaginary unit this because it's convenient. And it's easier to write this than it is to write that. And then I squared is defined as -1. So these are our two definitions. I is the square root of -1. I squared is -1. And from that, we can get all of our other powers of I. Let me tell you that this first little part that I'm going to do, pretty much everyone hates. And so there it is. That said, it's like the least important part of the section. And once I get past the little powers of I thing, the rest of the section is actually really straightforward, so don't let this first part frustrate you, hopefully. Okay, so with that disclaimer, here we go. I to the first, that's I, right? Same thing. I to the second, right here. I squared is -1. So those are our two definitions. So if I want to think about I to the third, I'm going to write this next part a little bit bigger so hopefully you can see it. That's I to the third is the same thing as I squared times I, because we would add our exponents, so that'd be I cubed. So I squared is -1, so -1 times I means this is the same thing as -I. So what we're doing is reducing I cubed to something simpler, which is -I. And then I to the fourth, that is I squared times I squared. Remember, I squared is defined as -1, so then -1 times -1 would equal 1. So I to the fourth is the same thing as 1. So that was kind of the worst of it. And then what we can do with that is every time we see an I to the fourth, it basically just counts as a 1. So here I have, and again, I'll write this a little bit larger just so it shows up better. So I'm just rewriting that. So if I have I to the fifth, it's I to the fourth with one extra I. I to the fourth is just a 1, and so I to the fifth is going to be the same thing as I. So I to the first. I to the sixth, that is I to the fourth times I squared. So I to the fourth is just 1, and then remember I squared was -1. So we're going to see this exact same pattern, I -1 and then -I1, because I to the fourth times I cubed, that's 1 times I cubed, and back here I cubed, -I, and then I to the fourth times I to the fourth, that's just 1 times 1, which is 1. So this pattern is going to repeat forever, I, -1, -I1. So what we can do with that is reduce other powers of I, so that's on the next page. Okay, so we're supposed to rewrite these powers in terms of I, -1, -I, or 1, which was our I to the first, I to the second, I cubed, and I to the fourth. So I to the 17th, I'm going to do this out the incredibly long way up here just to show you the why it works, and then I'll do the super short easy way. And then if you just believe the short easy way, that takes care of the confusing powers of I. And then we get to move on to the thing that isn't as bad. So I to the 17th. So remember from the last page, I to the 4th is 1. So if I think of this as, so there's an I to the 16 with a leftover 1. So I to the 4th 4 times. So I to the 4th, I to the 4th, I to the 4th, and one more I to the 4th. So that'd be 4, 8, 12, 16, and then one more would make 17. But for every I to the 4th, it's just 1 times 1 times 1 times 1 times I. So that means it's the same thing as I. So the less lame way to do that exact same thing is just to go 4 goes into 17 4 times. That was my 1, 2, 3, 4 pairs. And then 16, 1 left over, I to the 1st. So the remainder is always what the reduced power will be. So I to the 17th is the same thing as I to the 1st, which is just I. Here we have I to the 36th is the power up there. So if I go 4 into that power, 4 goes into 36 9 times, right? So that would just be like 9 I to the 4ths in a row. So 9 ones just multiplying each other. So I to the 36th, since it's divisible by 4, is just 1. I to the 43rd, so I will go 4 into 43. 4 goes in once, 4, 0, 3 doesn't go in. So it's 10 and 3 left over. So that means I to the 43rd is the same thing as I to the 3rd, which remember from the last page is negative I. And then lastly, I to the 62nd. So 4 into 62. And once you can kind of see 4 goes into 40 and there's going to be 3 left over, you don't have to do all this division. So if you know 4 goes into 60, you know there's going to be remainder 2. All you care about is what's the remainder. That's it. I'll go ahead and show the little steps here. So we're going 22, and then this goes in 5. And so then there's my remainder 2. So I to the 62nd is the equivalent to I to the 2nd, which is negative 1 by definition. Okay, and then the rest of the section is pretty much operations with complex numbers, which is pretty straightforward, it turns out. So first let's look at standard form for a complex number, and it's going to be this a plus bi. And a is called the real part, so all the numbers like 1, 2, 3, 4, 5, 6, 7 that we've known for all our lives, that's a. And then b is called the imaginary part, and that's where we're going to get this imaginary value I here. If b is 0, then a is a real number. That's what I was just saying. That's our numbers that we know and love. If a is 0, then bi is an imaginary number, and then together they make a complex number. So perform indicated operations, simplify, and then make sure our answer is in standard form. This is that standard form, so we're always trying to get to here when we're simplifying. And that said, there's a little bit of answer entry stuff, and we'll see some answers with fractions, but I'll show you that when we get there. So this first one is addition, and complex numbers do pretty much exactly what you would guess. They work just like terms. So if you kind of do whatever you're like, I think I would just do this, that's generally pretty much right with these. So this is our first complex number. These parentheses are just kind of showing it's two complex numbers, but math-wise, they're not really doing much there. So I'm going to write it without, and I'm going to go 4 minus 7i plus negative 5 is really just minus 5, plus negative 2i is really just minus 2i. It'll matter when it's a minus. And now I would add the real parts together and the imaginary parts together, and that's it. So 4 minus 5 is negative 1, and then minus 7i minus 2i is minus 9i. So you can really just think of it as collecting like terms, and that's exactly what you would think to do. This next one, so this is subtracting two complex numbers, and the same way that if this was 6 minus 7x, we would have to distribute that negative. It's exact same. So we'll rewrite this as minus 4 plus 2i minus 6 minus negative makes plus 7i. And now we'll just kind of collect up our like terms here. So this will be negative 10, 2, and 7 for 9i. Okay, for this next round, we are multiplying. And so much as you would do if this said minus 6x times 2x, it's basically the same idea. The negative 6 times 2 would make a negative 12. In the same way, x times x would be x squared, I times I is I squared. But then remember, I squared is negative 1. So every time we see an I squared, we have a little bit more work to do because we're not in standard form, which is a plus b I, no squareds on our i's. So this means we need to simplify where that's a negative 1, and now negative and negative flips that sign, and it becomes positive 12. So we'll see a lot of that as we do multiplication. This next one, we're going 3i times 4. So 3 times 4 would be 12, and then I comes along. Again, if you think of what you would do if it was an x, it's the exact same stuff. And then 3 times 5, so that'll be a minus 15i times I for I squared. And then this is really 12i minus 15, and that's a negative 1. So that's going to make 12i plus 15, which is right, but we should probably write it in the right order. So 15 plus 12i is the fully proper answer. This next one, so if it kind of makes you think FOIL, that's exactly right. That's what you do with it. So we'll just do out our steps. So we'll go 1 times 5 is 5. And on the outside, we're going 1 times 2i. And that is 2i. And then same thing with the inside last. So negative 3 times 5 for negative 15i. And negative 3 times 2 for negative 6. And then I squared. So this will be 5. 2 minus 15 is minus 13i, and then I squared there, so remember this is our negative 1, so it's going to flip that sign, which is what the I squared always does, is reverses the sign. So we'll make that a plus, and then 5 and 6 for 11, minus 13i. And now I'm in standard form, so that means I'm done. For this one, a couple of ways you can go. If you are good at doing perfect trinomial squares in your head, you can definitely do this out this way. Most people are not good at that. So I am going to show it as a FOIL. And then I will talk through how I would do the other version because it's something that you would just do in your head. So let me do the FOIL first. 7 and 7, 49. On the outside, we're going to get a 14i. And then we'll get the same thing on the inside. And that's why the formula goes 2ab, is because we get 2 of these. And then on the ends, we get 2 times 2 for 4, and I squared. So when we have something of this form, it's going to go a squared plus 2ab plus b squared. So the other way I can do this is go 7 times 7, 49. 7 times 2 would be 14, and then double it with this 2 from the formula, so that'd be 28. And if you look, there's my 14 and 14 for 28. And then 2i times 2i, there's the 4i squared on the end. And this time it's that I squared, so I'm going to write that minus 1 as minus 4. And then collect my terms, 49 and 4, and that would be 45 plus 28i. So you can either do this or just do the FOIL, and it comes out the same. Okay, complex conjugates. So conjugates are things like a plus b, a minus b. So that's conjugate pairs. Complex conjugate pairs, same thing, except now with complex numbers. A plus b, I, a minus bi. So normally when we FOIL these, right, these would come out to a squared minus b squared. And this is our, our difference of squares formula going the other direction. This is that a squared plus b squared that never factored. It's because it involved these complex values. So here, when I do my bi times negative bi, I would get negative bi squared. And then remember how I squared is negative 1. Oops, b squared, I squared, pardon me. And I squared is negative 1. So that's what ends up flipping that and changing it to the plus, is having those i's on the end versus the minus in this one. So anyhow, the short of it is, if you have complex conjugate pairs, you don't actually have to do out all the FOIL. You can just use this shortcut. So I will do the FOIL on this one just to show you why the shortcut works, and then I'll show you the shortcut afterwards. So here it is the long ways. 5 times 5 for 25. On the outside, we're going to get a minus 15i. On the inside, plus 15i. So that's where those always cancel. So that's why we don't need to do all that. And then here we're getting our minus 9i squared. So then 25, and then 15i plus 15i, those drop out. I squared is negative 1, and then negative 1 times negative 9 makes plus 9. So that's our 5 squared plus 3 squared that I could have gotten from right here for a squared plus b squared, 5 squared, and then b is, notice b doesn't include I, b is just the number in front of I, which is 3. And we get the exact same thing. So it just lets you skip over some steps, which is handy when we do division in a second. And so this should be 34. This next one, I'm going to do the FOIL on this as well, and then I'll show you the shortcut because people often get the shortcut wrong on this. So 4 times 4 for 16. So far, so good. On the outside, we get plus 4i. On the inside, we get minus 4i. So there's that canceling. And then here we get minus and plus. So that would be minus I squared. Those cancel. And then 16, and then minus, this is a negative 1, right? So minus a negative 1 would be plus 1. So there's our a squared plus b squared. The problem is people, instead of putting a 1 here, what I see people do a bunch is they'll go 4 squared, and they don't use the 1 in front of the I. They say plus I squared, which is then negative 1. It comes out 15, but it should be 17. So careful if you have one where it's just an I. B isn't I, B is the number in front of the I, which in this case is the invisible one. Okay, so what can we do with complex conjugate pairs? As it turns out, we can use them to divide. So if I have something like this, where I have 3 divided by a complex number, which I could think of it as 3, right, divided by a complex number, so it's division. How can I get this out of this denominator is sort of the idea. And if you remember the problems with the roots, we're rationalizing denominators, where say I had 3 over square root 5 plus 2. Remember the trick to that was to go root 5 minus 2. We would use the conjugate. Whoops, should be like that. Root 5 minus 2. We would use the conjugate because that cleaned up the radical in the denominator. We're going to do the same thing. Let me write this a little bit bigger right here. But we're going to use the complex conjugate. And that's kind of what this is showing. So for this one, we have 4 minus 2i. So I would want to use its opposite, still positive 4, but plus 2i. And then you'll see when I FOIL this, if I FOILed it out, right, that's what we just did on the last page, it's going to come out a squared plus b squared. It's not going to involve an I in the denominator, and so will be in standard form. So 3 times 4 up top would be 12, and I'm distributing, and so then 3 times 2 would be 6i. And then in the denominator, I'm going to use that shortcut. So 4 squared plus 2 times 2, or 2 squared. So up top we got 12 plus 6i over 16, and 4 would be 20. But then we have the issue that much like any other fraction, these things can reduce. And if you notice a value that divides in everywhere, that means you can simplify it. And again, it's that if you can factor it, you can cancel and then you can simplify. So if you think of it as taking a 2 out of the numerator, I would have 6 plus 3i. And then think of it as factoring a 2 out of here, I'd have 2 times 10, and those cancel. So when I'm doing it for me, I don't write all that. I just kind of go, okay, 2 goes into 12, 6, 2 goes into 6, 3, 2 goes into 10, sorry, 2 goes into 20, 10. And so that's a lot kind of cleaner for writing it, but this is the how come you can do that. And a couple more examples of that. So for this one, it's a negative 3 minus 4i. It's still negative 3. We didn't change the sign on the first number last time, so we still don't, even if it's a negative. So this would be its conjugate. And then from there, very similar. So we would be going 6 times negative 3 for negative 18, and then times 4 for plus 24i. And then the denominator, it'll be negative 3 squared plus 4 squared. And that will be negative 18 plus 24i over, that would be 9 and 16, so 25. And that, if you look, there's nothing that goes into, here I could factor out a 3, but it doesn't do anything with the 25. I can't divide out a 5, and this one's the limiting, so we can't reduce it any further. This one, same basic idea. The numerator is just a little bit more complicated this time. So 3 plus 4i, so our constant's going to be 3 minus 4i. And so this time we're going to have to do a little bit of FOIL for the numerator. So 2 times 3 is going to be 6. Outside minus 8i, inside 3i. And last is minus 4i squared. And then downstairs I'll use the shortcut, so 3 squared plus 4 squared. And cleaning up the numerator, 6, let's see, 8 minus 3 is minus 5i. And then this is I squared, so remember that's our negative 1, which makes this turn into a plus 4 from that minus 4. And 9 and 16 would be 25. And then let's see, 6 and 4, so that's giving us 10 minus 5i over 25. So here's one where it reduces, and this is where I would say, like I said, I could factor the 5 out, and that's why this works. For me, it's easier just to go 5 goes into 10 twice, 5 goes into 5 once, so invisible 1, 5 goes into 25 5 times. And that seems like an easy way to think about it.